Imagine you're transferring $100 to a friend. You hit send, the money leaves your account, and at that exact millisecond, the bank's server loses power. Is your money gone? To prevent your money from vanishing, databases use what's called a transaction. Look at this split-screen accounting ledger. We have account A with $500 and account B with $200. A transaction is a logical unit of work made of multiple steps. Here, transaction 1 reads account A, subtracts 100, writes the new balance, then does the same addition for account B. These steps must succeed or fail together as a single block. Let's watch it execute. The steps light up one by one. Account A drops to 400, account B rises to 300. Before the transaction, the total money in our system was $700. After the transaction, it is exactly $700. The math holds perfectly. Running operations sequentially like this is perfectly safe. But if an international bank processed transfers one at a time, the backlog would take years to clear. Systems have to run thousands of transfers at once, and that creates a specific engineering challenge. Modern databases use multi-programming to execute thousands of transactions concurrently. This means their operations have to interleave on a shared timeline. Here is a visualization of what happens when transaction 1 and a new transaction 2 both target account A at the exact same time. If we don't manage this overlap, things break. First is the lost update conflict. Watch the timeline. Transaction 2 reads the initial $500 balance. Meanwhile, transaction 1 finishes its work and writes a new balance of $400. But transaction 2 is still using the old math. It calculates its own update and writes $550. It completely wipes out transaction 1's completed work. That $100? Gone. Let's reset. The second danger is a dirty read conflict. Here, transaction 1 writes a temporary balance of $400. Transaction 2 reads that $400 and moves forward. But then, transaction 1 hits an error and rolls the account back to the original $500. Transaction 2 is now operating on a ghost value, making decisions based on invalid math. Reset once more for the incorrect summary conflict. Transaction 1 subtracts 100 from account A, but right before it adds that 100 to account B, a system audit runs. Transaction 3 calculates the total across both accounts. It misses the money in transit and reports a system total of $600. Left alone, interleaved transactions inevitably collide. Data gets overwritten, temporary errors become permanent, and the integrity of the financial system collapses. Let's test what we've covered. Look closely at this new timeline sequence. Transaction 1 updates the account, Transaction 2 reads it, Transaction 2 updates it, and then Transaction 1 fails and rolls back. Pause the video and determine which specific error is happening here. If you guessed a dirty read, you're right. The failure happens exactly here. Transaction 2 grabbed a value that was later reversed. It read uncommitted, dirty data. To solve these collisions, databases use concurrency control. Watch the timeline this time. When transaction 1 accesses account A, the database places a lock on it. Transaction 2 is forced to pause and wait. It cannot read or write until transaction 1 is completely finished and releases the lock. By mechanically blocking simultaneous access to the exact same data, concurrency control creates artificial isolation. The database can safely process thousands of overlapping actions while guaranteeing each one behaves as if it were the only task running. This brings us to the formal life cycle of a transaction. We can map out exactly how a database handles these requests. When a transaction begins its read and write steps, it enters the active state in this flowchart. Once those steps are done, it moves to partially committed. The math is finished, but the database is running its final safety checks. Once it passes, it moves to committed. The changes are permanently saved to the system log. But what if there's a system crash or a lock conflict? The transaction shifts to the failed state. From there, it is aborted. The database rolls back every single change to restore the exact previous state. This strict state machine ensures certainty. A transaction either makes it all the way to a permanent commit, or it aborts completely. It never gets stuck in a half-finished destructive state. All of these mechanical protections combine into 4 core rules for database reliability. Take a look at this graphic. We call these the ACID properties. A stands for atomicity, the all-or-nothing rule we saw in our first bank transfer. C is for consistency. A transaction must leave the database in a valid state, like ensuring our total ledger always equaled $700. I is for isolation. Thanks to locks, transactions don't interfere with each other, acting as if they are alone. And D stands for durability. Once a transaction reaches the committed state, the data survives, even if the power gets pulled seconds later. The ACID properties are the foundational engineering contract that allows us to trust digital systems with our money, our records, and our most critical data. This graphic summarizes the mechanics of database reliability. Take a screenshot for your